The word correlation would never seem like a new word to anybody because this is an English word that we actually use generally, literally in everyday English that we speak. And from the general standpoint of things, correlation simply means how you can know the relationship between two or more things, but it is usually locked down to two things. Now, from the statistic standpoint of things, correlation is the measure of the strength and direction of association or relationship between two numerical variables. So we should pay attention to key terms right here: strength, direction, and two numerical variables. What I'm trying to say right here is that correlation tells us the strength of association between two numerical variables. It means it tells us whether there is a very strong relationship between these two variables or not. It also tells us the direction of the association. It tells us the direction of the relationship. And the last important thing we have to pay attention to is to talk about the fact that correlation only occurs between two numerical variables. On the flip side, we have regression, which is a bit similar to correlation in some mathematical context, but something we need to know is that correlation is used to test the strength of association between two numerical variables, but regression can be used to predict one variable from the other. Hello everybody and welcome to another video, and in today's video we are going to be talking about the concept of correlation and regression. In today's video we are going to be talking about the types of correlation, how correlation works. We also talk about the types of regression and anything you need to know about the concept of correlation and regression when it comes to research and data analysis. So without further ado, let's get into the video. So now that we've defined the concept of correlation, it only makes sense for us to know what we use to quantify correlation. Yes, correlation is a statistical term also, and we try to quantify it the best way we can. And the number that we use to quantify correlation is known as a correlation coefficient. A correlation coefficient is a single number that we use to define the strength and direction of association between two variables. Now, this number can be denoted with several letters, okay, because it is a variable. But I think from the statistics standpoint of things, we use the Greek letter rho to represent a population correlation coefficient, and we use the Greek letter, I think R, not Greek letter, but we use R to represent the sample correlation coefficient. But in several things, in several materials or articles on the internet, people sort of like interchange it. They use it interchangeably, so you can use rho, you can use R, but the main point is that we can use a single number to actually quantify the correlation between two variables. So that now leads us to the first important thing we have to talk about: the types of correlation. So basically we actually have three types of correlation. We have what we call the positive correlation, we have the negative correlation, and we have the zero or no correlation. So let's talk about this thing extensively. So a positive correlation occurs whenever two variables are actually changing in the same direction. This simply means that if one of the variables is increasing, the other is actually increasing also, or if one of the variables is decreasing, the other is also decreasing. A typical example of two variables that follows a positive correlation is usually the purchasing power and income. So what do I mean by that? The more you earn, the more you can purchase or buy something. So there is actually a positive correlation between your purchasing power and your income. Now, the next type of correlation that we are going to be talking about is what we call the concept of the negative correlation, and it is just like the opposite of the positive correlation in the sense that for negative correlation, the two variables are actually changing in the same direction. So what do I mean? It means that if one of the variables is increasing, the other variable is actually decreasing, or if one of the variables is decreasing, the other variable is increasing, and that is just it. A typical example of two variables that have a negative correlation between them is the law of demand, which simply states that the higher the price, the lower the quantity demanded. So that means if you increase the price of your commodity, definitely the quantity that can be purchased or that can be bought must actually reduce in nature. So that means there is an inverse relationship when it comes to negative correlation, and we have a direct relationship when we come to the concept of positive correlation. Now, when it comes to zero or no correlation, the definition or the information that you need is inside that name. It means there is literally no form of association, there is literally no form of correlation between these two variables, and that's just it. So examples of two variables that are, that have zero correlation or they are not correlated is, I can say, my age and my CGPA. My CGPA in school should not affect my age, or my age should not affect my CGPA, and it all makes sense like that. Now, I've mentioned that a number can be used to quantify the concept of correlation coefficient, but I think the next question you're going to be asking me is that, so does this number have a range? Does it follow a specified pattern? And the answer to your question is yes. The correlation coefficients actually have a number, and it ranges between -1 all through 0 and down to +1, with -1 and +1 being included in the range. So what does that mean? It simply means that the lowest value that your correlation coefficient can take is actually equals to -1, and the highest value in quotes that your correlation coefficient can take is actually +1, and we have 0 in the middle. So the closer you are to +1, the stronger the positive correlation that you have, and the closer you are to -1, the stronger the negative correlation that you have. So let's say, for example, we have r is equals to +0.35 and we have r is equals to 0.85. Now, r is equals to +0.85 is actually a very strong, or we can say a strong positive correlation, and r is equals to 0.35 is also a positive correlation, but in this case we classify it as a weak positive correlation. So that simply means that as you get closer to 0, the correlation, either positive or negative, gets weaker. The same thing can be said with negative, in the sense that r is equals to -0.95 represents a very strong negative correlation, okay, and that's fantastic. And r is equals to -0.10 represents a very weak negative correlation. We also have the likes of moderate correlation, which simply means something like, let's say, r is equals to -0.57 or r is equals to 0.59. These are moderate, negative, and positive correlations respectively. It means that they are just in the middle. They are not too strong and they are not too weak at the same time. Now, it is actually possible for us to diagrammatically or visually represent the strength of association between two variables, and the tool or the aid that we use to actually bring this coefficient to life is what is known as the scatter plot or the scattergram. Now, the scatter plot consists of the horizontal axis and the vertical axis, and in between these two axes we have a point of intersection, that is a point where the two variables that we are talking about, maybe x and y or something, they actually intersect. So let's say we have variable x, some values here, and we have variable y, some values here. Then we can plot a scatter plot for these two variables, where we can actually see if there is a positive correlation, a negative correlation, or a zero correlation. So what I'm trying to say is that for positive correlation we have a scatter plot for it. And what does the scatter plot in this case look like? It simply have like a positive slope, or I can say it's sort of like forms this line, this straight line slope, upward straight line slope. Now, the stronger the positive correlation, the more closer this line tends to be linear, and the weaker the positive correlation, the weaker the lines that we can see. Now, for a negative correlation, there is always this downward slope, like sort of, okay. Now, the stronger the negative correlation, the more we can see a visible straight line that has a downward slope, and the lower the negative correlation, the weaker the line that we can see, okay. And for zero correlation, there is no form of association. We cannot be able to pinpoint a line, that is, we can't draw a line of intersection between these two variables. Now, we call this line the line of best fit. Very important. Now that we've talked about the concept of correlation coefficient and the concept of scatterplot or scattergram, it only makes sense for us to talk about the types of correlation that we have. And basically, we have two types, but some can say we have three types. So I'll assume we have three types right here. We have the Pearson's correlation, we have the Spearman's ranking, and we have the points by serial correlation. Now, the last one is a bit, it's not popular. It's something that is not really being mentioned, but it's still a type of correlation. So let's talk about these things individually. Now, the Pearson's correlation is actually the most popular form of correlation. In fact, everybody one way or the other must have actually come across this type of correlation. And what does it entail? The Pearson's correlation is actually used to test for the strength of association between two numerical variables. So what am I trying to say? I'm trying to say that the Pearson's correlation is a quantitative approach to correlation. In fact, some scholars actually say that we use the concept of Pearson's correlation whenever we are working with a normally distributed data, and that is right. So that means if you are trying to test for the significance of your correlation coefficient, okay, and you are assuming normality condition, meaning you are using your parametric test, then the Pearson's correlation is the correlation type that you're supposed to use in the context here. Okay, now the second type of correlation is what we call the Spearman's ranking, and the Spearman's ranking is a less accurate in quotes version of the Pearson's. Okay, I'm not saying they are the same thing, they both have different formulas that guides them, okay, but just that the Pearson's formula or the Pearson's correlation is a quantitative approach to correlation, but the Spearman's ranking is a qualitative approach to correlation, in the sense that the Spearman's ranking uses the position of each of the variables in our data set to get correlation, whereas the Pearson uses the actual value, the measured value of each of the variables to get the correlation coefficient of the two variables that we are talking about. So it simply means that the Spearman's ranking is basically used when you are working with non-parametric tests. So let's say you performed your Mann-Whitney U test, okay, regarding your data set, and you want to now get the correlation, or you want to test for the significance of correlation between the two variables that you are working with, then definitely you are going to be using a Spearman's ranking. Now the points by serial is like a mixture of the Pearson's and the Spearman's ranking, in the sense that the points by serial can be used to actually test for the relationship between a categorical variable and a numerical variable. So that means the points by serial is taking the categorical aspect of the Spearman's ranking and is taking the numerical aspect of the Pearson's correlation and combining them together into just a single correlation type. Now that we've talked about the concept of correlation and every single thing that we need to know about it, it's time for us to talk about regression. From the simplest standpoint of things, regression is actually a statistical technique that is used to predict one variable from the other variable. As simple as that. So what I'm trying to say is that from the simplest standpoint, or from the basic standpoint of things, regression is defined by only two variables, and it is very important for us to know the variables that we are talking with. So whenever you want to work on regression, or you want to build a regression model, okay, you have to know what we call the dependent variable and the independence variable, and that is going to determine the type of regression that you are going to be working with over time. So the independence variable is the variable that is not depending on other variables for its value to change. In fact, for the independence variable, all other variables depends on it. Okay, now we use the letter X to actually represent the independence variable. Now it have other names which I can't remember right now, but I'm going to like just drop the list right now so you can just check it out. You can pause and just view it. Now on the flip side, we have the dependence variable, and this is a variable that its value depends on the value of the independence variable. Now we use letter Y to actually to denote the value of the independence variable, and it also have other names which for some weird reasons I still can't remember right now, but I'm going to be listing them right here. I think your dependence variable is also known as the response variable, the target variable. Okay, I can remember those ones. And I think your independent is also known as the, I think your factor. Yeah, it has several names. If you're building machine learning models, your independent is also known as the feature. Yeah, so it depends on the context that you are actually working with. So it makes sense right now. Whenever you're now working with a regression whereby you have just one dependent variable and you have just one independence variable, you're working with what we call a simple linear regression. As simple as that. Now, one thing that defines the linear regression is that there must be a linearity condition. We are assuming that there is a straight line condition. We are assuming that there is a linear relationship between the two variables that we are working with. So that is one of the very key defining features that defines simple linear regression. So number one, we must have just a single dependence variable, and we must have just a single independence variable. Now the regression equation for a simple linear regression is given as y is equals to ax plus b. Some scholars will say y is equals to bx plus a. Anyhow you write it, you're fine. In fact, some can go as far as saying y is equals to mx plus c, which is basically just the equation of a straight line which is still correct. Okay, now for a simple linear regression, the equation is y is equals to ax plus b, where y obviously represents the dependent variable, x represents the independent variable. Now the value beside the independent variable, either a or b, but in this case of ours, I can use m or I can use a, represents the slope, and the c or the b represents the intercept, which can either be a positive value or a negative value. Now we have formulas that can help us calculate the value of a or m, which is the slope, and the value of c or b, which is the intercept in this context. But we are not interested in how to calculate this, because whenever you use softwares to build regression models, the software is going to provide you each of those values straight up. All you have to do is to just provide the value of all of your x variables and all of your y variables, and the software is going to help you get the respective values of a and b, or I can say the values of slope and the intercept. So this is the first type of regression that we are going to be meeting. Now the second type of regression that we can obviously meet is a better version of the simple linear regression, and that is what we call the multiple linear regression. Please note that the condition is still linear, meaning that for multiple linear regression there must be a linear relationship between a dependent variable and the independent variables. Now I said independent variables because for multiple linear regression we are going to be having multiple values of independent variables. That simply means that at least two variables. So we have just a single dependent variable, which is y, and we have multiple values of x. We can say x1, x2, x3, x4, and so on. Now this is where it gets interesting, because we have a lot of conditions that defines the multiple linear regression, and in this case we are going to be having individual slopes regarding individual independent variables. So that means, for let's say we have a multiple regression that has 3 independent variables, so we are going to be having y is equals to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus, and then we put what we call the error term. Now, and that is just the flexibility in quotes that defines the model, because you are predicting with regression and you don't really have the actual value in the long run. So you're going to be having predicted value, and when something is predicted from an original value, error will actually occur, but the goal is to reduce this error as simple as possible. Now the simple linear regression and the multiple linear regression are the most popular types of regression that we have in the world of statistics and machine learning. Okay, but there are other types of regression. We have the likes of polynomial. This is basically used when there is no linear relationship between the dependent variable and the independent variables. Okay, we also have the likes of the Bayesian regression, where we actually bring in Bayesian statistics to actually be the building factor of our model, because the regression model, either multiple or linear, is basically based on the OLS. So that is the ordinary least square method, but instead of using the OLS to be the mathematical backup of our regression, we are bringing in the Bayesian statistics to do that. And we also have other types of regression like the lasso regression, we have the ridge regression, we also have the binary logistic regression, we have the nominal regression, we have the ordinal regression, and so much more. Now the honest truth is that I have actually made a video about all other types of regression in detail, defining the conditions that allows us to build them, and so much more. So I'll be linking that video either here or anywhere right here, so that you can just check it out and watch it. And that is all about the concept of correlation and regression. Now you can also take your analysis a bit further by saying that after getting the correlation between two variables, you can test for the significance of this correlation. So that simply means that if you are having a positive correlation between these two variables, are you sure that this correlation you are having, is it by chance, is it by luck, or it is an actual correlation? Then you can perform a test on correlation coefficient. You can also perform the same test on the slope of regression. So that means if after building a regression model and you have the value of your slope and your intercept, you can actually perform a correlation test on each of these values to test their significance. Okay, some of these softwares, not even some of these softwares, any software that you use to build regression model will obviously help you to perform tests on all of these things. You can see the p-values that are attached to each of those values in the long run whenever you use softwares to build your regression model. We can also perform hypothesis tests on the significance on the predicted variable that you have with your regression equation or your regression model. So y is equals to b1x1 plus b2x2 plus b3x3. Your y is your dependence, your y is your independent variable, and at the same time it is still the predicted variable. Now your predicted variable, the value you get can actually be tested, and you can actually see whether there is a significance in this value that you had or not. Now there are several ways to visualize the output of regression models, and one of the most important plots that we use is what we call the residual plot, and this is just a plot that shows the difference between the actual value and predicted value, okay, and stuff like that. Now these are a bit of, I won't say advanced, but higher levels of regression informations that we can actually have, but maybe in subsequent videos I will actually take my time and touch this in quote advanced part of regression. Thank you very much, and we'll see you in the next one. Bye for now.